Okay, this is the third video for chapter 6. And the first two videos, excuse me, we learned continuous random variables are different. We needed a new approach, and we learned two alternative approaches. One is based on the cumulative distribution function, and the other is based on the probability density function. So now we cannot use just one point or listing all possible outcomes. They don't work. And we are going to use these things. And we will apply this idea to the normal distribution. Okay, let me introduce the normal distribution here. As I said, the normal distribution is the most important distribution in any science, in social sciences, natural sciences, engineering, statistics, whatever. All right, I think 99% of scholars would agree with that, right? So in natural science, surprisingly, many phenomena follow normal distribution, like heights and weights of animals and plants, right? And velocities of the molecules in the ideal gas. So I don't know what they mean actually, but I don't know why the normal everything is following the normal distribution. And what's interesting here is a binomial distribution was derived on the assumptions, under some assumptions, like which is more intuitive, more realistic experiments, but the derivation of normal distribution is purely mathematical. So I'm not going to derive under what assumptions we obtain the normal distribution, but surprisingly, it is mathematically derived, but in the end, it is everywhere. The resulting distribution can be found everywhere, right? Not only in natural science, but in social sciences, normal distribution is commonly assumed. So, like for example, when you get test scores in a standardized form, that is using the assumption that the distribution is normal. So then standardization makes sense. And if you're interested in finance, you may have heard about Black-Scholes equation, which is to find the optimal, like the appropriate price for option value pricing. In doing that, it assumes that the asset price is normally moving, like distribution is normal. So every so the distribution in the future distribution of an asset is normal, then you can evaluate an option like call option, put option. If you have heard about financial derivatives, they involve options. And then how can we price them? That is based on Black-Scholes equation. They are Nobel Prize winners, and they also assume normal distribution of asset prices. And Six Sigma, you may have heard about this, like because GE, the legendary CEO at GE, used this principle. Like Six Sigma means in the normal distribution, you don't allow error up to that Six Sigma distance. So 99.999% accuracy is represented by Six Sigma. Later you will see what it means. Sigma is standard deviation of a normal distribution, and up to 6 sigma we are going to make the control the quality. So anyhow, it also assumes normal distribution. So normal distribution is everywhere, not to mention statistics. So from now on, I'm going to introduce how normal distribution is used in statistics in this chapter and the following chapters. Okay. So as I said, I'm not going to derive the normal distribution, how the normal distribution is derived, and the formula is very complicated. It is you don't need to memorize that. You can just find the formula on Wikipedia, but it is very strange format. Um, But the main point here is the normal distribution is parameterized by two numbers, the mean and the variance. Of course, the variance is always strictly positive. So given the mean and variance, you can like draw the bell curve. You may have heard about the bell curve. And we write x, a random variable x, follows normal distribution with parameter mu and sigma squared. So as the variance is denoted by sigma squared, so standard deviation is usually denoted by sigma. Okay, the reason why we put square is because sigma stands for standard deviation. Or the notation can be simply like n. Instead of writing normal, you can just write n, then it means normal distribution. And maybe you must be familiar with this type of graph, bell curve. So fixing the variance, if you change the mean, the shape is the same. It is parallel shift, you know. So the mean determines the center, the peak. The peak is the center, is at the center. So blue one is centered around 0 because the mean is 0. And green is centered around -1 following its mean. And orange is around 1, its mean. So mean is the center, and then the bell curve goes smoothly and nicely away from the center, symmetrically. Okay? And now fixing the mean, if you change the variance, it is about the flatness. If the variance is small, the green one is most concentrated, like peaked at the center, always peaked at the center. But if the peak is high, the variance is small, so a lot of probability is dense. Probability is dense around the mean. But when the variance increases to 2, it is flatter. The probability is more evenly distributed on the tail. So it is like decreasing slowly from the center. So peak, as I said, again, the mean determines the center and the variance determines the slope. How quickly the probability decreases as away from the center. Okay. So, but still, in any case, it is always symmetric, always smooth, always like a nice bell curve decreasing away from the center. So, a few basic normal distribution facts. By the way, the bell curve is the PDF, probability density curve, probability density function for the normal distribution. So, bell curve is the PDF. And it is always symmetric about mu. So because of the symmetry, the median is the same as the mean. The median is also mu, right? And the mode is also mu. The peak is at the center, so the mode is mu. So mean, median, mode are the same. And it ranges between plus minus infinities. As you see, like, so even though the bell curve goes to 0, but it never touches the 0. So there is a small probability everywhere up to infinity, right? So the range is infinity. Probability, as I said, probability always decreases away from 0. It approaches to 0 but never equals to 0. And, change in mu, change in the center makes parallel shift. And increase in sigma is about the slope, right? So you basically understand how the normal distribution looks like. Okay, so in the following chapters, all the random variables will be approximated to a normal distribution. Normal distribution is the only distribution you will need, right? So we need to learn how to calculate probability from the normal distribution. But the problem is it is not that easy because, as you see, it looks smooth and nice. That is actually more that makes calculating the area more complicated, right? So it requires computer. Wikipedia gives you a formula for the PDF, but even if you know the formula, it is nearly impossible to calculate that, like integrate the function. So uh, we are going to use a computer, Excel, basically Excel, and there is another problem. Given, well, like there are two parameters, mu and sigma, and depending on those parameters, the probabilities will be different. So it is not easy to handle all the possible cases. So what we are going to do is, first, we will start from the standard normal distribution. So normal distribution with 0 and 1, like mean 0 and variance 1, or the standard deviation is also 1. This is a special case of the normal distribution. And we will call this standard normal distribution. And we are going to reserve z as a special notation for standard normal distribution from now on. So whenever you see z from now on, it is almost always a standard normal distribution. So you can write z follows normal distribution with mean 0, variance parameter 1. And we will first study how to calculate standard normal distribution. We are in the past, when I was a student and like when I first arrived here, when I first started teaching this course, I used to use a paper table, a table on a paper, but it's nearly obsolete. Instead, you may use Excel, or you can search for standard normal distribution calculator on Google. Then you will see a lot of nice calculators. If you enter a certain number, that it returns PDF or CDF. Okay. So I am going to use Excel. On Excel, it uses the CDF of the standard normal distribution. We will study how to calculate the CDF of a standard normal distribution on Excel. I am going to, as an exercise, I will find these 5 CDFs from Excel, right? So f-2, f-1, f0, f1, f2. Let's find them. f-2, what you are going to do here is norm, norm dot s dot dist. It returns the standard normal distribution, right? And then arguments you have to enter is z, which is this value, -2, and cumulative or cumulative option. If you put true, it will return the CDF, cumulative probability. But if you put false, it will return probability density. Probability density is not a probability. It is just density, as I said. So what we want is cumulative probability. If you calculate that, if you enter that, it returns 0.02275. If you click percentage, it is about 2%. And if you extend decimal points, it is about 2.275%. Similarly, let me do this in the same way. norm.s.dist, norm, standard distribution at -1, and cumulative option is true, then you are going to get this. And change to percentage, and you get 15.866%. That means below -2, you have only 2.275%. This is probability below -2. And below -1, there is 15.866%, right? So in the same manner, you can keep going. And interestingly, below 0, of course, there must be 50% because it's symmetric above 0. Because the distribution is symmetric, positive side and negative side should have the same probability. So below 0 is 50%. I will. So I calculated CDFs for all of these, all 5 numbers. You get 5 CDFs from Excel. This is how you calculate probability from standard normal distribution probability from Excel, right? So we get these numbers. So from here, use these 5 information and try to find probability that standard normal distribution is greater than or equal to -1. You may use this information, or you may just try this from Excel, but that Excel does not have formula for this probability. So try to use this. I'm going to give you the answer in the next video. Okay? Thank you for watching. See you later.